The key to simplifying any radical expression is to identify the index. In this case, since there is no index, it is assumed to be a 2. So what that means is we are looking for groups of 2 sets of factors in order to remove 1. So if I look at the square root of x to the 5th, what I'm really looking at is x times x times x times x times x, a total of 5 factors of x underneath the radical. And I need groups of 2 of them. Well, how many groups of 2 do I have? I have 2 groups of 2. So that's going to be an x for each of them. So it's an x here times an x out here. And then the square root symbol is still there with an x underneath. But we can simplify what's out here by taking x times x and making that x squared. So the square root of x to the 5th is really x squared radical x. We can double check this always by raising what is outside to the power of the index and then multiplying by what's in here. So we can do it this way too. We'll take our simplified answer here and raise it to the power of the index. X squared is x to the 4th. The square root of x squared is just x. X to the 4th times x equals x to the 5th, which was our original radicand. So we know that this simplified version is correct. Same thing here. We have the square root of y to the 9th. There is no index indicated, so we have to assume it's a 2. So y to the 9th is really looking at a string of 9 factors of y. I've got, and I'm looking for groups of 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got one group of 2, 2, 3, 4 groups of 2. So for each of those 2, I get a y outside. So this is going to be 1, 1, 1, and 1. And they're going to be outside, and there's going to be 1 left over. So that's going to be y to the 4th radical y. If I wanted to check that, I would take that to the second power. I would raise it to the power of the index. Y to the 4th squared would be y to the 8th. The square root of y squared would just be y. Y to the 8th times y would be y to the 9th, which was my original radicand, so I know that I've simplified this properly. Now a to the 13th, I'm not going to draw all these out here again. The idea is that if my index is 2, I'm looking for how many groups of a are there if I'm looking for groups of 2. So if I have 13, I'm really taking 13 divided by 2, which would be 6. So I'm going to have a to the 6th. I'm going to have 1 left over underneath. All right, there were 13 factors of a here, just like there were 9 here. I was looking for groups of 2, so I'm really taking 9 divided by 2, which is 4. And then there's 1 remainder underneath. Up here, I had 5, and the index was 2, so I'm taking 5 divided by 2, which is 2, with a remainder of 1 underneath. So now here, when it's 13, I'm going to do the same thing. I'm going to take 13 divided by 2, which is 6, with a remainder of 1. That goes underneath. To check this, I would take a to the 6th radical a, raise it to the power of the index. A to the 6th to the second power would be a to the 12th. The square root of a times the square root of a would just be a, and a to the 12th times a would be a to the 13th, which was my original radicand, so I know that I have simplified this properly. Same thing here, but now my index is 3. So if I were to simplify this, I'm looking for the cube root, and I have 1, 2, 3, 4 factors of x, and 1, 2, 3, 4, 5 factors of y. And I'm looking for groups of 3. So if I take groups of 3, I can only take one x outside, and I'm going to have an x left over underneath. I'm leaving room here because now I'm going to look at the y's. I'm looking for groups of 3 y's. I have one group of 3 y's, and I have 2 y's underneath. So this whole thing now simplifies to xy radical xy squared. To check that, I would raise this whole thing to the power of the index. Of 3, and it should be correct. So xy to the 3rd power, well, that would be x to the 3rd, y to the 3rd. And then I'm going to multiply that times xy squared to, that would be the cubed root, sorry. The cubed root of xy squared to the third power would just be x y squared. So x to the third times x would be x to the fourth. Y to the third times y to the second would be y to the fifth, and that was my original radicand, so I know I have simplified this properly. Now we would do the same thing here, except we have a coefficient. So the cube root of 27 is 3. That comes outside the radicand. A to the fourth, and I'm looking for groups of 3 where there's going to be one group in A to the first, and there's going to be one A stuck underneath there, because there were 4 factors of A's, and I took 3 of them out as one group, leaving one behind. The B6s, there are 6 B's under there, and I'm looking for groups of 3. Well, there are 2 complete groups of those, so that would be a B squared. So now I have simplified this to 3AB squared radical A, and I can always check that by raising it to the power of the index. 3 to the third power would be 27. A to the third power would be A to the third. B squared to the third power would be B to the sixth, because we multiply. And then A, again, this is a cubed root here, sorry. The cube root of A cubed would just be A, so that A times this A to the third would be A to the fourth. So 27, A to the fourth, B to the sixth, which was my original radicand, so I know I have simplified this correctly.